Okay, so I have heard that there are some questions you guys have about your lab, and this is a piece of paper I have photocopied on my front desk, and I want to use this as a way to talk with you about your lab. All right. Now, much like your lab, you know what your reactants are because you were told what to mix, what you had to put together, what you had to heat, whatever it was that you're supposed to do, you know what those are. Now, what's missing in each of these is I'm not indicating if it's a solid, liquid, gas, or aqueous. You do need to do that in your lab. Another piece of information you already have is that there are 5 reaction types that we've learned about. We've learned about synthesis reactions. The synthesis ones are where you take several reactants and make one bigger product than what you had before. All right. There's decomposition reactions where you have one reactant that will break up into several different products. These are your single and double replacement reactions. Single replacement reactions and double replacement reactions look very similar. The only difference between them is in double replacement, they're 2 ionic compounds and you form 2 different ionic compounds. And in single, you only have 1 ionic compound and a single element, and you end up with another single element in a compound. And the last one here is combustion. In combustion, you always identify by having oxygen as one of your reactants, along with a hydrocarbon, and your products are always going to be carbon dioxide and water. All right, so we're going to work our way across this list. We're going to look for things that are synthesis reactions. We're going to look for things that are double replacement, decomp, and so forth. All right. So when you have a synthesis reaction and you're doing your lab, you would know that that's the case because you only made one product. You only tested for and identified one product that was being made. All right. So things that would be easy to locate that would be a single product formation would be something, in this instance right here, where I specify that you only made one product, right? So these 2 things you tested for and you only found one product. Oh, and look at that, our product is a base. So the idea here with the base is that whenever a base is formed, all right, what you ended up with is that there was some kind of metal of some charge and it's attached to a hydroxide ion. Okay, that's what it is you formed. So if we go back to the question that we have here, we have to take a look at what would be our metal, right? And this is a little bit of a tricky one because when you look through these, none of these are considered metals. But when I say the word metal, I'm really talking about a positively charged ion. And if you go back to the sheet that we learned about our ions, right? There is a positively charged ion on here that is not a metal, that is made of the same elements that we have in the equation that we're focusing on. Did you see how I focused it on it? So this is nitrogen and hydrogen, and we have hydrogen available that what we can make is an ammonium ion. There's our metal. And our metal will combine with our hydroxide. All right, so there's our hydroxide. And this has to be the formula of our product that we made. Because we only made one product, and we knew that it was a base. And the base tells us this is our basic setup. So we have to go back to our reactants and the atoms that are available to us. And we can see that NH4 is the only positive ion we can make from that. Oxygen and hydrogen for our hydroxide is there. And now we work on balancing it, okay? So if you take a quick look through this, you're gonna see there is 1 nitrogen, 3 plus 2 is 5 hydrogens. This one has 4 plus 1 more is 5 hydrogens. 1 oxygen, 1 oxygen. This one is already balanced for us. So that is how you predict a product when it's a synthesis one, right? When you know you're making one product. And in this case, we needed to know that it was a hydroxide that we formed. All right? All right, let's do a decomposition reaction. Decomposition reactions, we said, is something that breaks apart to make many things. All right, so let's go down here to number 11, because you can see we have one single ingredient here, one reactant, and what it has to make is at least two things. All right, so part of what we would have to do is, like when you did a lab, you would have to identify something you know about your products. And in this case, we would have done a splint test. And our splint test, when we put it in, would have made our splint glow brighter, or the flame glow brighter. So what gas must we have formed? Hopefully you guys said oxygen. And as you recall, oxygen is one of our diatomic atoms. So we have to write it as O2. And then we did not form another gas, because that's the only thing that happened was that the splint would have gotten brighter. And if you would have looked in your container, maybe, let's say we found a liquid, all right? Not another gas, but a liquid. So we have to go back and look at our ingredients, okay? What do we have available to us that could make a liquid out of this? All right, what if we tested with litmus paper? And the litmus paper did absolutely nothing. The red stayed red and the blue stayed blue. That would mean the thing that we made is neutral, right? So it can't be an acid, it cannot be a base, it has to be a liquid and made of these atoms. Maybe I've given you guys enough information for you to realize that the thing we would have made was water. All right? So here we're showing that hydrogen peroxide breaks apart and decomposes. We would have tested for this. We could have potentially tested for this and found it to be neutral. And now we've decided, based upon the atoms that were present, what our products would have been. All right? And now you go ahead and do your balancing. Notice there's 2 plus a third oxygen here, making an odd number of oxygens on this side, where this side can only have even number of oxygens. And since this oxygen right over here is making everything odd, I am going to put an even number in front of it. So I'm going to have 2 waters. So I have 2 oxygens, plus 2 oxygens is 4. So I'll put a 2 here, and that will give me 4 oxygens. And then we can see we have 4 hydrogens here and 4 hydrogens here. So this is balanced. Again, the one thing I am not writing in on this are those symbols for solid, liquid, gas, and aqueous. That is all something you guys will do with your lab. All right? All right, so there's an example of how one predicts a synthesis, how one predicts a decomposition reaction. We're going to do a single and also a double replacement. So remember, I told you single and double replacements look a lot alike. The thing that makes them different is a double replacement reaction. You have to have 2 compounds. And in a single replacement, you only have 1 compound with a single element. So we're going to go right here in the middle of the page. You can see there's a compound, metal and a nonmetal, and another compound, metal, nonmetal, right? Single or double replacement reaction. Hopefully you guys are saying double. And if you watch my other video that I showed you, when you have double replacement reactions, you also want to use this paper. All right? Remember, this is the one that helps you predict what your products are like when you have a double replacement reaction. So we're going to go back to this. Sodium is our metal. Sodium is a +1 charge. Sodium is going to go with the negative charge over here, which is chlorine. So since sodium is +1 and chlorine is -1, we're going to make NaCl. And that meant that calcium, which is +2, is going to go with the phosphate. Our phosphate's a -3 charge. So calcium being +2 is going to attach to a phosphate that's -3. Oops. And so you're going to need 3 calciums for every 2 phosphates to make this electrically neutral. All right? So we focus on our negative ion, going to this paper here. Our chloride is with sodium. So we look across. Sodium is not listed on this first line, so we go to the second line, and it says that it's soluble. So when something's soluble, we say it's aqueous. And now we look at the next one. We look at the negative ion, phosphate. Our phosphate's with calcium. So read down our line. Phosphate is with calcium. That's not what we have here, so we go to this one. and it says not soluble, right? So phosphate with any other positive ion is not soluble, because calcium is not an alkali ion. Remember, if we want to know our alkali ions, they're listed right there at the top for you. So it's going to say not soluble. So not soluble means we put down a solid, and this reaction goes on, and we produce a precipitate and an aqueous solution. As for balancing, calcium, we have 3 calciums here. So I'm going to put a 3 in front for 3 calciums. There's 6 chlorines. So I'm going to put a 6 in front of here to get 6 chlorines. We have 6 sodiums. So over here I need to put a 2 in front to have 6 sodiums. And then there's 2 phosphates, and this one already had 2 phosphates. So this one's balanced. So that's the double replacement reaction. Our next one is the single replacement reaction, which looks a lot like it, but in this case, what we have is a single element and a compound. And in single replacement reactions, the element that's by itself pushes out of compounds the element that is like it. What I mean by this is iron is positively charged. We don't know what charge it is. Over here I'm telling you, you can make it a 2 or a 3, because we know iron can be a 2 or 3, so I'm going to give you some flexibility on that. When this, we know chlorine's negative, and when we have an acid, hydrogen's positive. So that means that the iron has to push the hydrogen out, and the hydrogen ends up being by itself. Now we would have done a splint test with this and tested it, and our splint test would have shown that the gas popped, it made a little barking sound, and that would have confirmed that hydrogen gas is formed. And hydrogen, like oxygen down here, is one of those elements that are always diatomic, right? So if hydrogen pushes, it gets pushed out by the iron, then that means iron will connect with the chlorine. And the formula that we write with the iron and the chlorine is dependent upon the charge of your iron. All right, so we'll just say that our iron was +2. You could do this with +3 if you wanted. It makes no difference. So if iron is +2, this is a +2 charge, chlorine's -1, you're going to have 2 chlorines with that iron. All right, as for balancing, 1 iron, 1 iron. This one has 2 chlorines, so put a 2 in front of here for 2 chlorines. That gives us 2 hydrogens, and this also has 2 hydrogens. So that one's balanced. So again, I'm talking through how we figure out what's over on the right-hand side here. And sometimes it's because we know something about it with the litmus paper, if it was acid or base. Sometimes we'll know something about it because of a gas that's produced, like this. Sometimes it will be the fact that we tested it and it was neutral, or we just happen to see that there was a liquid present. This one, we didn't do any testing at all whatsoever. I didn't talk about anything other than the fact that if this is a double replacement reaction, we should have formed a solid, a precipitate. So if you did a test and you saw little solid pieces forming or some cloudiness forming, that's your precipitate that formed inside your reaction. All right? And then the last one we haven't talked about yet is our combustion reactions. And combustion reactions, from your notes that you had, you always make carbon dioxide and water. So if you're always making carbon dioxide and water, your ingredients have to have carbon, hydrogen, and oxygen in them, right? You have to have carbon, hydrogen, and oxygen in them. We'll take a look at this. Here's a carbon, hydrogen, oxygen molecule that in the presence of oxygen would probably burn. And if it burns, we're going to make carbon dioxide and water. And we would have tested this with a splint test, and our splint would have gone out. And water would be something maybe we look for droplets, or you might see a gas that might be coming out, or you may not see it at all if it was gaseous. If it was evaporated away, we may not have been able even to see in that water. All right? And then you work on balancing. So every one of these on this sheet are things that you can predict your reaction type, but you have to understand that it's going to be one of these 5. And there's something about the ingredients, the reactants that you have here, that are clues to what your products are going to be because of just the setup of these and then also because you know what it is that you formed. All right, so I'm going to just leave you with this. I'm also leaving an answer key with the teacher in class. And so if you want to practice some of this before you actually do your lab, that would be good. And good luck, everybody.